I have a motor here in that fan, but I also have a generator. In every single motor, electric motor, you will find built in a generator. You can't get around it. And it's not a bug, it's a feature. Okay? Let's think of the coil inside of an electric motor. I want that coil to turn all on its onesies. Okay? So I very cleverly figure out how to make the current go exactly the way I want it to, and that would be this way, so that the dipole would be anti-aligned with the external magnetic field. I do that because that dipole is going to want to line up, and that's going to turn the coil. Okay? Now, as soon as that coil gets lined up, I switch the direction of the current using those commutators, those brushes, if you will. But that's done through engineering. That's done by design to make it turn. But as soon as that loop starts to turn in the external magnetic field, suddenly I'm changing the number of field lines through the loop. And that's going to cause a second current, an induced current, and it's going to be in the opposite direction of the battery current. How do I know that? Because the battery current is trying to make it turn, and the induced current is trying to fight that turn. And so the induced current is going to give me a dipole in the opposite direction. This red one's trying to line up. That's what's turning the motor. The green one is fighting it. And you can see that as it turns, I get right here, and now the green one would be helping, and the red one would be fighting, but I use the commutators to change the red one, and nature changes the green one. Pow! And now the red one's helping, and the green one's fighting. Again, I get to this point, the commutator changes the red one, nature changes the green one. Okay? Now, this is a feature. Let me explain what I mean by that. If I have a motor, and that motor has a coil with 4 ohm resistance, and I plug it into the wall, V equals R, 120 volts with 4 ohms gives me a current of 30 amps. That's huge. You don't want 30 amps going through anything for very long. And it doesn't go through the motor for very long, just until the motor starts turning. Then you get this second current, the induced current, that's opposite the direction. We call it a back EMF, a voltage that's fighting the wall voltage. So now when I use V equals IR, I got 120 volts trying to make it turn. I've got 118 volts trying to stop it, and that gives me I times 4 ohms. This is 2 volts equals I times 4 ohms, or I is equal to a half amp. Now, you know from 205 that once I get something spinning, it just wants to keep spinning. That's the natural way of things. So when I've got a motor, I have to work to get it to start spinning, but once I get it started, I just have to fight friction, and it'll keep going. Well, it turns out that when you plug in a motor, before it starts turning, you got 30 amps going through the coils. That's a lot of torque that's getting that thing going. But once it starts spinning, once it gets up to speed, you get this back EMF, so that really all you got going through is half an amp. And that's all you pay the company for, is half an amp. And that's what's required to overcome the friction. Now you know that if you've got an electric motor, say in a hairdryer in your bathroom, if suddenly that hairdryer jams, what's the next thing to happen? It bursts smoke, and then it bursts into flame. Because once it stops turning, you no longer have that induced current, you no longer have the back EMF, and suddenly you got 30 amps going through a device that was only designed to handle half an amp. And it's going to melt in your hand, not in your mouth. Okay? So, we've run out of time. We'll talk more about this on Monday. Have a great weekend, and bless you people.